Hi everyone, I'm Ujjwal. I'm a PhD student at the National Center for Radio Astrophysics. I'm also a member of the Spotlight collaboration. And today I'll be talking about turning the spotlight on fast transients. Basically, I'll first go through what FRBs are. I will try to go through this quickly because I'm assuming most of you know what these objects are. These are transient events in the radio sky. We have about 854 of them detected till now. These are broadband events. We have detected them from 110 megahertz to 8 gigahertz. These are bright. They have brightness temperatures of 10 to the power 36 kelvins or more for typical parameters. We believe these are of extragalactic origin. Earlier, we only knew this from the dispersion measures, which is the electron density along the line of sight. But then we got the first localizations from which we confirmed that these were indeed extragalactic sources. The first detection was in 2007, the Lorimer burst. And then we detected the first repeating fast radio burst in 2016 called the Spitler burst. And we found out that there are two types of these sources. Some only emit once, whereas some emit repeatedly. Mostly, we have not seen a lot of periodicity with these FRBs. And 58 such repeaters have been detected till now, and about 118 such FRBs have been localized to their host galaxies. So you can see the Lorimer burst in this plot here and the Spitler burst in this plot here. You can notice a difference in structure, which we'll come to next. So they have very high brightness temperatures, which automatically implies that these are not emitting incoherently. These must be coherent emitters of radiation. And so this indicates that, again, yeah, because they emit coherently just like pulsars and other objects that we have seen already. And so what we do is we try to narrow down their emission mechanisms by studying their emission properties. These include spectrotemporal properties like, for example, multiple components or drifting subbursts or band-limited emission. And we also study their polarimetric properties and a lot of temporal microstructure that these bursts have shown, including microsecond level structures as well. And so the progenitors are still unknown except for FRB 2024-0428, which was traced to a magnetar in our own galaxy. So apart from the fact that we are studying FRBs for their own sake, we are also studying FRBs because they are cosmological probes. So because they are extragalactic sources, they can trace the intergalactic medium along a line of sight. So, and we can use them to constrain missing baryons. Again, we have gone through the school, so you know some of these things. They can be used as traces of dark energy. They can be used to constrain reionization histories, calculate the Hubble's constant, curvature of the universe, dark matter, and so on. Many of the applications use the DMZ relation, which you can see in this plot from Liam Connor's latest paper. And you also use them to probe the intergalactic medium itself via propagation effects like scintillation, scattering, dispersion. Yeah, so now that is done, now we can go on to the Spotlight project. Again, Jayanta introduced it as well, and you have already seen Harsha and Mikhaila's talks. So I will go through this quickly as well. Spotlight is a commensal survey for FRBs, pulsars, RRATs, LPTs, and so on with the GMRT. What we are doing is we have built a dedicated backend so that we can observe all of these in real time. It's funded by the National Supercomputing Mission and consists of 60 Rudra servers and 90 NVIDIA 100 GPUs, which makes it a petaflop level computing system. So it has a data rate of 24 gigabytes per second for voltages and about 6 gigabytes per second for beamform data. And we are forming 2000 post-correlation phased array beams on the sky. Again, as Harsha and Michael have shown in their talks, the advantage is that these beams suppress RFI and systematics in your data. And a large number of beams give you a wide FOV, which improves your service speed. So we can localize an FRB to a particular beam out of those 2000 beams. That gives us an arc minute or sub-arc minute localization. And we can further localize it using imaging, which will give us an arc second or sub-arc second localization. So these are our survey parameters. So our time resolution is fixed to 1.3 milliseconds. We are covering a frequency range from 300 to 1460 megahertz. This corresponds to bands 3, 4, and 5 of the GMRT. Our bandwidth can either be 200 or 400 megahertz, depending on the band and the setting that the user has done. So, and our theoretical fluence limit is 0.2 Jansky milliseconds for a burst detected at a signal-to-noise ratio of 10. We expect to detect about 300 FRBs in the 3 years of operation that Jayanta mentioned in his talk across all 3 bands. And we will be able to localize events to arc second precision by imaging these bursts in real time. And we will also dump baseband data at Nyquist resolution for every event that we detect. So this is a comparison of Spotlight with other FRB surveys. Some surveys are missing, my apologies. I try to keep these parameters updated, but again, if your survey is not represented properly here, let me know. So of course, we have to talk about chime. They are observing over 400 to 800 megahertz and can localize down to milliarc seconds now due to their out triggers. But earlier, they could only do up to 15 to 30 arc minutes with their baseband data that they had recorded. Their fluence limit is quite high, and that is true for a lot of the other surveys. We can see from this particular table that Spotlight has a frequency coverage that is comparable or greater than most of the surveys in this table, and our localization accuracy is also comparable or better than a lot of the surveys shown here. Yeah. So this is our current status. We deployed Spotlight in open sky and commensal modes in the current cycle, which is that just ended, which is GTAC cycle 48. So we gave 100 hours to the scientific community to use the Spotlight backend for their proposals, which we are calling open sky time. And the rest of the time we were observing in commensal mode. So we supported 160 beams throughout the cycle. And we were commensal for about 50% of all observations in this cycle, keeping all of those things in mind that we are using a smaller number of beams and are active for only half the time. We predicted that we would detect about 1 FRB in this cycle. Again, fingers crossed. So, and we were recording data to disk and processing it offline because our real-time pipeline was not yet ready. And this automated pipeline is called Word0. And it is on GitHub and was deployed as a temporary measure until our real-time pipelines come online. So this is the flowchart that everybody is showing, which covers the entire Spotlight system. I won't go through the details, but I will be talking about the transient search part, which comes after both Harsha and Mikhaila's modules. And so this is a flowchart for the real-time pipeline. Okay, I will try to take through this slowly because it's a bit complicated. So the data comes in from the correlator beamformer in ring buffer that we call telescope shared memory. And then it goes into a larger ring buffer because the first one is too small to do any search. We put it into a larger ring buffer called FRB shared memory. This is about 400 seconds of data that we retain in memory at a given time. Between these two modules, there is a module that we will develop called Arachne, which will inject fake FRBs while our data is coming in so that we can test the pipeline, generate data sets for machine learning and so on. Then it all goes to our actual real-time pipeline, which starts with RFI mitigation, de-dispersion, single pulse search, peak filtering, and then all of these other modules, which I'll talk about soon. So our current trigger rate is about 1 per minute, but we need a trigger rate of 1 per 10 minutes. So we need some improvement in some of the modules, which people will talk about in subsequent talks. So yeah, so I will now go through the pipeline stage by stage. So this is the RFI mitigation module. As you can see, this is data without any RFI mitigation taken from the Spotlight backend in band 4. And then we apply RFI mitigation using one of PulsarX tools called Filtool. And almost all the RFI goes away, and you can see the pulsar single pulses quite nicely. And so this is the RFI mitigation that we will also use in our real-time pipeline. After that, after the data has been RFI mitigated, we will do de-dispersion. So again, we have discussed this in the day one of the school as well. When the signals travel through the interstellar medium, they will have something called dispersion, which we have to correct for before we search for them. And so AstroAccelerate, which is the GPU-based pipeline we are using, will do de-dispersion and single pulse search in one go. And so it will make something called a DM transform, which it will then search for single pulses in. We have a DM range from 0 to 2000 parsec per centimeter cube, about 8,500 DM trials. We are going to extend it up to 4,000 parsec per centimeter cube in band 4 and about 8,000 parsec per centimeter cube in band 5 without any issues. And so after the DM search is done, we will do a single pulse search. So currently we have a threshold of 6 sigma for our single pulse search. Currently the maximum width we are searching for is 0.5 seconds, but eventually we will extend that to about 10 seconds. And the single pulse search itself can generate anything from 1,000 to millions of candidates per beam. And so then we go to peak filtering. So AstroAccelerate internally has a peak filtering setup where what it will do is arrange all candidates in a DM time plane and then drive through 2 stencils, a 3x3 and an 11x11 stencil through the data, and anything within one stencil would be a one candidate. So as in if there are 5 points inside a stencil, they'll be treated as a single candidate. And so through that, as you can see, it kind of thins out the herd and the number of peaks go down. And so this brings the number of candidates down as well. After AstroAccelerate is done, we move to the second half of the pipeline. So what we have done is that AstroAccelerate, this part of the pipeline and this part of the pipeline are independent. So in the sense that they use separate GPUs, and once one is done, the job is given to the other pipeline, and then the first half of the pipeline can analyze the next block of data. And so we then do clustering. The clustering algorithm is currently quite simple. We use something called DBScan, which again you guys used in day one. And we just do clustering in the DM time plane for every beam. Then after we do that, and some additional filtering is done, which Kshitij will talk about in his talk, we get a list of candidates for which we extract two features, the D-dispersed dynamic spectrum and the DM transform. These two features are necessary to do for the classification, classifier to do the classification. And so then we go to our classification module, which is we are using fetch. And so that uses these two features and two CNNs, two independent CNNs, to classify it as an FRB or RFI. One change that we have done compared to the way it's usually done is instead of YOR, which you used in day one, we are using something called Candies. So Candies is essentially our own implementation of YOR, where we wanted to, one, accelerate things further on the GPU, and two, we wanted to make the DM transform a bit clearer because YOR was made for high frequency telescopes. And so the DM transform there can be very unclear, it can be quite narrow. And so the classifier will often look at that and think it's RFI. But what we do is we do a zooming in into the DM plane so that the bow tie pattern becomes clearer and we can get better results from our classifier without doing any change to the classifier itself. Yeah. So after that, we do candidate optimization. Again, Kshitij will cover this thoroughly in his talk, so I won't talk about this. And so I will leave you with this slide. So this is the single pulses from pulses that we have detected till now. We have seen that we are reaching our theoretical fluence limit from our current observations in this cycle, which is good news. And we can clearly see a lot of detections, which is also good news for us. Now we are just waiting for our first FRB detection. Thank you.
Thank you, Ujjwal. Questions?
Thanks. Lovely talk and great project. I had two questions. One was you mentioned that currently your trigger rate is 1 per minute, but your ideal is 1 per 10 minutes. I don't understand that statement. Is that because you're just picking up too much RFI, or why is 1 per 10 minutes better than 1 per minute?
No, so 1 per 10 minutes is our ideal trigger rate. So that's the trigger rate we can handle given our capabilities, as in the kind of data, the amount of data we can store and so on. So we need it to be 1 per 10 minutes, but currently it's 1 per minute because of RFI. Yes, we don't really have RFI mitigation deployed just yet. So as soon as we get that deployed, and it will be much better.
So that you're resource limited, so you can...
Yeah, because we have only 2 petabytes of storage, which I know sounds absurd because it's 2 petabytes, but at the rate of 1 trigger per 10 minutes, we can store all of the data without any issues. If it's greater than that, we will have issues with storing the data as well. So that's the kind of... Yeah.
Okay, understood. Yeah. And the second question I had, this Candies code, is that publicly available? Is it?
Yes, it's on GitHub, yeah. I have a tendency to put all my codes on GitHub, and I typically open source everything I do. So yeah, Candies is one of those. It's up on GitHub.
Right, and I guess there is a GitHub link somewhere. I just look at
it is. It is there in the slide, but yeah, I will share it. Yeah, done.
Hi, Ujjwal, nicely presented, well presented talk. Thank you. I was having 2 questions. One is related to the false detections. How many false candidates you get to see in the normal run? I mean,
we do false, as in false negatives, right? Yeah, we do get some of them because again, we have seen that again something that we have talked to with Devansh as well, who is the author of Fetch. We are seeing quite a bit of both false positives and false negatives with fetch. Typically, it's false negative, so there will be FRBs that fetch should classify, pulses that fetch should classify that are just removed. But we have a fair set of false positive as well. So the idea is to retrain fetch, yeah, so that we
There's
can.
one more question. You show a nice picture of the peak detection using repeating FRB signal. How often in real situation you get to go back there and do some control observation?
I'm a bit unsure what that. Sorry. Yeah, I didn't catch that purpose. Sorry. Yeah.
It's a commensal mode observation.
Yeah. Of
Unless
course,
you
yeah.
have a time, you can't steer the antenna to some direction. So if you were to do on the repeating FRBs.
Yeah. Oh, we had repeating FRB observations, but we didn't have a lot of luck. So we would have detected something there, but somehow we didn't have that much luck. We could detect it.
No, so Prabhu, I think that's
what
one
I
point,
think
but I think you are asking that if you find a repeat, if you find a burst, and what is the possibility to find a repeat burst?
No, just as a control check for the system, are you able to go every day or once in a week, go back to some known?
Yes. So currently, I think that's what Ujjwal was saying.
Yeah.
Currently, what we have done as a control test, we have looked for pulsar, we have looked for crab jan pulses, and then also the repeating FRB observation has mostly happened because of some running proposal, mostly by us, like Ujjwal and others.
Yeah.
And then by the time, in simultaneous to that, we run the spotlight projects and then look for burst. But we are a little unlucky to find a repeat burst in that time.
Yeah. And we are also unlucky in that respect that we don't have a lot of repeating FRBs which are active right now. So a few of them only. Yeah.
One last.
Sure. Yeah, sure. Go ahead.
If somebody reports a FRB detection and they tell you the time and direction, do you have a chance to go back to the archive? Do you keep any information that will be useful to do post analysis?
Okay, so currently we have a commensal system. So technically the answer should be no, but we have a proposal in mind where if we have an interesting source in our field of view, we will make a beam on it and record data. So that way we could probably do it, but otherwise we are commensal. So we are terribly dependent on what the users are doing. GMRT users are doing.
Just a little bit add just for a minute.
Sorry,
that in that there is a VO system is getting set up by one of our engineered GMRT. So where the aim is that we actually real time try to accept the triggers which is coming from external world. We'll queue them in our observing system. It happened to be in our field of view. Chances could be rare because GMRT field of view is not very high. We'll immediately steer one beam towards that or a couple of beams toward that. If it is not happen to be in our field of view, we'll queue our observing system, and whenever GMRT see that spy, there'll be a beam formed towards that. So we are building up that kind of strategy. Yeah.
But otherwise, we are a commensal system, so we are terribly dependent on what the user is doing.
Any other questions from anyone else in the audience? Okay, so if not, let's thank Ujjwal and move on.